Welcome to Science for Sleep, where we slow down the universe and gently explore the biggest questions it has to offer. Tonight, I want you to imagine something vast, a future so distant that every star has faded, every galaxy has thinned into darkness, and even black holes, the most powerful objects in existence, have finally disappeared. No light, no motion, no structure, just an endless, quiet expanse. And in that stillness, a deeper question emerges. If nothing changes anymore, does time still exist? Tonight, we will journey far beyond the lifespan of the sun, beyond the death of galaxies, beyond the evaporation of black holes, and into the final eras that physics predicts, where entropy reaches its maximum, energy spreads thin across an expanding cosmos. Oh, and the universe becomes so calm that the very meaning of before and after may begin to dissolve. This is not just the end of the universe. This is the question of whether time itself can end, and what that would truly mean. Before we can ask how time ends, we must first understand what time is. It sounds simple. We feel time constantly. Seconds pass. Days turn into years. Memories accumulate behind us while possibilities stretch ahead. Time feels like a river moving in one direction, carrying us from birth to death. But that feeling, so familiar, so intimate, may not be what physics means by time at all. In everyday life, time is measured by change. A clock ticks. The earth rotates. Atoms vibrate inside cesium clocks, defining the modern second. We measure duration by motion, by cycles, by repetition. Without change, there would be nothing to measure, no events to separate, no before and after. So already we see something important. Time is deeply connected to change. If nothing changes, what does it mean to say time is passing? Physics offers multiple answers to what time is, and none of them are entirely simple. In Newton's universe, time was absolute. It flowed uniformly everywhere, independent of space, independent of matter, independent of observation. Even if the entire universe were frozen, Newton's time would continue to march forward. But that picture did not survive the 20th century. Einstein showed that time is woven together with space into a single fabric: space-time. Time does not tick at the same rate everywhere. It slows down near massive objects. It slows down at high speeds. There is no universal cosmic clock. Each observer carries their own measure of time along their path through space-time. And yet, even in relativity, time still exists as a dimension. Events are ordered. Causes precede effects. World lines trace histories from past to future. But then, thermodynamics introduces something else, the arrow of time. The laws of physics at a microscopic level are mostly time-symmetric. If you reverse the equations of motion, they still work. But entropy, the measure of disorder, introduces asymmetry. Entropy increases. Systems move from order to disorder. Ice melts. Stars burn fuel. Structures decay. This is why we remember the past, but not the future. The early universe began in an extraordinarily low entropy state. Over billions of years, entropy has increased. Stars formed, burned, and died. Matter clumped into galaxies. Black holes grew. Energy spread out. Entropy gives time direction. Without entropy increasing, there would be no arrow. And this is where our question deepens. If the universe eventually reaches maximum entropy, if all energy is evenly distributed and no further change can occur, what happens to time then? Because if time is tied to change and change stops, does time still have meaning? Imagine a universe trillions upon trillions of years from now. No stars remain, no nuclear reactions burn, no gradients of temperature exist to power processes, no structure forms. Every region looks statistically identical to every other. In such a universe, nothing meaningful happens. No clocks tick because ticking requires energy differences. No memories form because memory requires physical change. No observers remain to mark duration. In that state, does time continue? Or has time effectively ended? Not by stopping, but by becoming irrelevant. There is an important distinction here. The end of time does not necessarily mean a sudden halt, like a clock frozen mid-second. It may mean something quieter, a gradual fading of meaningful sequence, a universe that continues mathematically but loses physical events. Time may not end with a bang. It may end with stillness. But before we travel that far into the future, we must clarify something else. Time has at least 3 layers. There is psychological time, the way humans experience it. There is thermodynamic time, the arrow defined by entropy. And there is relativistic time, the dimension woven into space-time geometry. These are not identical. Psychological time depends on consciousness and memory. Thermodynamic time depends on entropy gradients. Relativistic time depends on geometry and motion. The end of time might mean different things depending on which layer we are discussing. If conscious observers disappear, psychological time ends. If entropy reaches maximum and nothing changes, thermodynamic time loses direction. If space-time itself evolves toward some final state, relativistic time may continue mathematically, but with no events left to mark it. This layered complexity is why the question is so profound. When we ask whether time ends, we are really asking whether change ends, whether structure ends, whether causality ends, whether sequence itself dissolves. In everyday experience, it feels impossible for time to stop. Even when you sit perfectly still, your heart beats. Your cells metabolize. Earth rotates. The galaxy moves. The universe expands. Time feels unstoppable. But physics suggests that the universe has a long-term trajectory toward simplicity, toward equilibrium, toward a state where energy differences vanish. And without differences, nothing happens. Without happening, nothing marks time. Perhaps time does not need to stop to end. Perhaps it simply needs to become empty. In the coming chapters, we will trace the cosmic timeline forward, through the death of stars, through the evaporation of black holes, through the fading of matter itself. We will watch entropy rise and structure dissolve. And at the very end of that journey, we will return to this question. If the universe reaches perfect equilibrium, if no gradients remain, if no event can distinguish one moment from another, is there still a moment? Or has time quietly faded into irrelevance? For now, we stand at the beginning of that journey. Time still flows, stars still burn, energy still moves. But the clock of the cosmos is ticking towards something vast and quiet, and understanding that destination requires understanding time itself, not as a feeling, but as a physical phenomenon. Because the end of time is not mythology, it is a scientific possibility, and we are about to follow its logic to the very edge of the universe. To understand how time might end, we must first understand how physics defines it. For most of human history, time was assumed to be simple. It flowed uniformly everywhere, independent of events. Whether stars moved or stood still, whether planets formed or collapsed, time would continue at the same steady rate. Isaac Newton formalized this idea in the 17th century. In his view, time was absolute. It flowed equably, without relation to anything external. It did not depend on motion. It did not depend on gravity. It did not depend on observation. Even if the entire universe froze in place, Newton's time would continue. It was a universal clock, a backdrop, an invisible metronome ticking beyond the reach of change. But in the early 20th century, that certainty dissolved. Einstein revealed something deeply unsettling. Time does not flow the same everywhere. Time slows down when you move quickly. Time slows down in stronger gravitational fields. There is no single universal now that applies to the entire universe. Instead, time is woven into space itself, forming space-time, a four-dimensional structure where distance and duration are intertwined. In this framework, time is not separate from the universe. It is part of its geometry. Each observer carries their own clock along their path through space-time. Two observers moving differently will disagree about how much time has passed between events. A clock near a black hole ticks more slowly than a clock far away. A clock aboard a fast-moving spacecraft ages more slowly than one on Earth. Time is relative, and yet it remains real. Events still occur in sequence. Causes still precede effects. World lines still extend from past to future. But relativity introduces a concept that challenges our intuition even more deeply: the block universe. In the block universe interpretation of space-time, the past, present, and future all coexist within a four-dimensional structure. Just as all locations in space exist simultaneously, and all moments in time may also exist simultaneously, laid out across space-time. The flow of time, in this view, is not a fundamental feature of the universe. It is a feature of our consciousness moving along a world line. From this perspective, time does not pass. It simply is. The entire history of the universe, from the Big Bang to its farthest future, exists within the space-time structure. If this interpretation is correct, then the end of time does not mean a final ticking clock. It means reaching the final boundary of the space-time manifold. But here, we encounter something subtle. Even in relativity, time is still part of the structure. It may be relative, but it remains embedded in the geometry of the universe. Events are ordered along time-like paths. Causality remains intact, so even if stars die and galaxies fade, a space-time itself could, in principle, continue to extend indefinitely, unless something else intervenes. Because relativity describes time geometrically, but thermodynamics gives time direction, and quantum mechanics introduces uncertainty. The equations of relativity are largely time-symmetric. They do not distinguish between forward and backward time. If you reversed every motion in the universe, the equations would still hold. But entropy does not behave that way. Entropy increases, and that increase defines the arrow of time, which means that time, as we experience it, may not be fundamental. It may be emergent from entropy. If that is true, then time could fade when entropy reaches its maximum. Not because space-time geometry disappears, but because nothing changes within it. So we now have three layers of time emerging in physics. First, geometric time, the dimension within space-time. Second, thermodynamic time, the arrow defined by entropy. Third, experiential time, the perception created by memory and change. The end of time could mean different things depending on which layer we consider. Geometric time may continue as long as space-time exists. Thermodynamic time may end when entropy reaches equilibrium. Experiential time may end when observers disappear. Already the question becomes more nuanced than it first appeared. We are not asking whether clocks will suddenly stop. We are asking whether the universe will reach a state where time loses meaning. Because meaning requires difference. Difference requires change. Change requires gradients. And gradients require structure. If the future of the universe is one of gradual smoothing, of energy spreading thinner and thinner across an ever-expanding cosmos, then the gradients that drive change will fade. The cosmic clock will not shatter. It will unwind slowly, quietly, almost imperceptibly. And this unwinding begins with expansion. In the next chapter, we turn our attention outward to the accelerating universe itself and begin tracing the timeline forward. Because if we want to understand the end of time, we must follow time to its most distant horizon. And that journey begins with the expansion of space itself. If relativity tells us how time is structured, thermodynamics tells us why time has direction. Because without direction, there is no ending. At the microscopic level, most physical laws are reversible. If you recorded 2 billiard balls colliding and played the footage backward, the motion would still obey Newton's laws. The equations would not complain. They do not inherently prefer forward over backward. Yet, in everyday life, we never see broken glass reassemble itself. We never see smoke return neatly to a candle. We never remember tomorrow and forget yesterday. The difference lies in entropy. Entropy is often described as disorder, but more precisely, it is a measure of how many microscopic configurations correspond to a macroscopic state. A highly ordered system has few configurations. A disordered system has many. The second law of thermodynamics states that in an isolated system, entropy tends to increase. This increase gives time its arrow. The past is low entropy. The future is higher entropy. Now, the reason we remember the past is because memory formation increases entropy. The reason we cannot remember the future is because it has not yet unfolded into higher entropy states. But this raises a profound question. Why did the universe begin in such a low entropy state? The early universe, shortly after the Big Bang, was incredibly hot and dense, yet remarkably uniform. That uniformity corresponds to extremely low gravitational entropy. Matter had not yet clumped into stars, galaxies, or black holes. It was smooth. Over billions of years, gravity amplified tiny fluctuations. Gas collapsed into stars. Stars forged heavy elements. Galaxies formed. Black holes grew. Structure emerged. With structure came entropy increase. Ironically, the formation of stars and galaxies, which appears to create order, actually increases total entropy because radiation and heat are dispersed in the process. Entropy is subtle. It does not simply mean chaos. It means energy becomes less available to do work. This is the key. Time, as we experience it, depends on usable energy gradients. Hot regions next to cold regions. Dense matter next to empty space. Chemical imbalances that allow reactions. Life itself depends on entropy gradients. Stars shine because their cores are hotter than surrounding space. Heat flows outward. Energy becomes diluted. Entropy increases. When those gradients vanish, nothing happens. And here is where our journey begins to take shape. The universe is expanding. As it expands, matter spreads out. Radiation stretches. Temperature differences diminish. Over vast timescales, stars burn their fuel. Galaxies exhaust their gas. Black holes swallow remaining matter. Entropy rises, but entropy cannot increase forever. There is a maximum, a state of thermodynamic equilibrium. When the universe reaches that state, no further work can be extracted. No further gradients remain. Everything is uniformly cold and thin. This is called heat death. Heat death does not mean fiery destruction. It means equilibrium. No differences, no flows, no processes. And without processes, what distinguishes one moment from the next? In such a universe, geometric time, as described by relativity, may still exist mathematically. Space-time coordinates may still extend forward, but thermodynamic time, the arrow defined by entropy, would lose meaning, because entropy would no longer increase, it would be maximized. This is why the end of time is often linked to heat death, not because clocks break, but because nothing happens. Imagine a cosmic stillness so complete that no event distinguishes 1 second from another. No particle interaction changes the overall state. No observer remains to mark duration. Would we meaningfully say time is passing? Or would time be indistinguishable from timelessness? This is not speculation pulled from fiction. It is the logical extrapolation of thermodynamics applied to cosmology. And current observations suggest the universe is accelerating in its expansion due to dark energy. That acceleration pushes matter farther apart, reducing interactions even more quickly. The arrow of time continues to point forward. Entropy continues to increase. But it is pointing toward quiet, toward dilution, toward a state where difference dissolves. And since difference defines time's direction, the fading of difference suggests the fading of time's meaning. Yet there is a long journey between now and that final equilibrium. Stars still shine. Galaxies still collide. Black holes still merge. The arrow of time still drives complexity. But complexity is temporary. And in the next chapter, we begin tracing the cosmic clock forward, not millions, not billions, but trillions of years into the future, to the era when stars themselves begin to vanish. Because the end of time does not begin with an explosion. It begins with the slow fading of starlight. If the arrow of time is driven by entropy, then the engine of entropy in our current universe is stars. Stars are the great furnaces of cosmic change. They fuse hydrogen into helium, releasing energy that flows outward into space. That energy creates gradients, hot next to cold, radiation moving into darkness. Entropy rises. As long as stars shine, time has direction. But stars do not shine forever. To understand the end of time, we must understand the end of stars. Right now, we live in what cosmologists call the stelliferous era, the age of stars. It began a few 100 million years after the Big Bang, when gravity pulled hydrogen gas into dense regions that ignited nuclear fusion. It will last for trillions of years more. But even trillions are not forever. Star formation depends on cold hydrogen gas collapsing under gravity. Over time, galaxies use up their available gas. Each generation of stars locks hydrogen into heavier elements. Supernova explosions redistribute material, but the supply gradually diminishes. Already star formation in our universe is slowing down. The peak of star formation occurred billions of years ago. The cosmos is, in a quiet way, aging. Red dwarf stars, small cool stars, are the longest lived. Some may burn for up to 10 trillion years. They sip their fuel slowly, efficiently. Long after our sun has died, red dwarfs will continue to glow. But even they will exhaust their hydrogen. And when they do, no new stars will replace them. Because the universe is expanding. Expansion does something subtle yet profound. As space stretches, galaxies drift farther apart. Distant galaxies recede faster and faster due to dark energy. Eventually, beyond a certain horizon, they will recede faster than light relative to us. Not because they're moving through space at superluminal speeds, but because space itself is stretching. In the far future, observers in our galaxy may see no other galaxies at all. The cosmic microwave background radiation will redshift beyond detectability. The night sky will grow emptier. Expansion isolates structure, and isolation accelerates the decline of interaction. Stars form from dense clouds of gas. But as galaxies exhaust their supply, and as expansion prevents new gas from flowing inward, star formation ceases. One by one, stars will die. Massive stars will explode as supernovae within millions of years. Medium stars like our Sun will swell into red giants and shed their outer layers, leaving white dwarfs behind. Small red dwarfs will slowly fade into dim stellar remnants. After approximately 100 trillion years, star formation will effectively end. The universe will enter a new era. No more new light, no more fresh fusion, no more birth of stars. The sky will not go dark instantly. It will dim gradually. White dwarfs, the cooling cores of former stars, will radiate residual heat for quadrillions of years. But they will not generate new energy. They will only release stored heat. And as they cool, entropy continues to rise. Each photon emitted carries energy outward, spreading into an ever-expanding cosmos. The universe grows colder and thinner. Here is the subtle connection to time. Time is not powered by clocks alone. It is powered by processes: nuclear fusion, gravitational collapse, radiation flow. When these processes slow, the arrow of time weakens, not in direction, but in intensity. The universe becomes quieter, more static, less dynamic. Imagine a future civilization living around a red dwarf star 5 trillion years from now. The sky would already look emptier than ours. Most galaxies would have drifted beyond view. Cosmic background radiation would be faint. Star formation would be rare. They might wonder if the universe was always this sparse. They might never know about the cosmic richness we see today. Eventually, even red dwarfs will exhaust their fuel. When the last star dies, perhaps around 100 trillion years from now, the stelliferous era will end. The cosmos will enter what scientists call the degenerate era. No active stars, only remnants. White dwarfs cooling toward invisibility. Neutron stars slowly radiating away residual heat. Black holes quietly dominating galactic centers. The end of time has not yet arrived, but something essential has shifted. The primary engine of entropy, stellar fusion, has stopped. From here onward, change slows dramatically. Without stars, the universe loses its brightest sources of complexity. Chemical reactions diminish. Planetary systems freeze. Life, as we understand it, becomes impossible. Time continues, but it becomes thinner, less eventful, more silent. And the silence deepens over unimaginable spans. The expansion of the universe ensures that structures become increasingly isolated. Galaxies gravitationally bound together may merge into a single massive structure, but beyond that, expansion separates everything else. The cosmic web stretches until interactions between distant structures cease entirely. Entropy keeps increasing, but the rate of noticeable change slows. The universe drifts toward equilibrium. In the next chapter, we will enter the degenerate era, a time when the cosmos is populated not by bright stars, but by the faint embers of stellar remnants. Because the end of time is not triggered by the death of the last star. It is deepened by what remains afterward. And what remains is colder, darker, and far more patient than anything we can easily imagine. After the last star has burned out, the universe does not end. It quiets. The bright, dynamic, stelliferous era, the age of stars, gives way to something slower, darker, and far more patient. This next chapter of cosmic history is known as the degenerate era. The name comes from degenerate matter, the exotic states that remain when ordinary atomic pressure is no longer supported by nuclear fusion. White dwarfs, neutron stars, and black holes dominate this era. They are not luminous engines of creation. They are remnants. By roughly 100 trillion years from now, star formation will have ceased. The universe will contain only the cooling cores of once bright suns and the collapsed husks of massive stars. White dwarfs will slowly radiate away their stored heat. For quadrillions of years, they will glow faintly in the infrared, gradually dimming. Over unimaginable spans of time, perhaps 10 to the power of 15 years and beyond, even they will cool into what are sometimes called black dwarfs. Cold, dark spheres of carbon and oxygen, invisible against the cosmic background. Neutron stars, dense remnants of supernova explosions, will persist even longer. Their intense gravity compresses matter to extraordinary densities. They too will slowly radiate residual heat and spin down over vast timescales. And then there are black holes. At the centers of most galaxies reside supermassive black holes, millions to billions of times the mass of the Sun. In the degenerate era, as galaxies merge and gravitational interactions settle, black holes will dominate the gravitational landscape. Stars may no longer shine, but gravity still operates. Over trillions upon trillions of years, gravitational interactions will cause stellar remnants to be ejected from galactic cores. Close encounters between remnants will transfer energy, flinging some objects into intergalactic space, while others spiral inward towards central black holes. The universe becomes a scattering of cold, dense objects drifting in expanding darkness. Time continues to pass. But what defines it now? There are no new stars forming, no fresh nuclear reactions, only slow gravitational dances, occasional collisions, gradual cooling. Entropy continues to rise. Each interaction disperses energy further. Each radiation emission spreads heat thinner across expanding space. The arrow of time still points forward, but it moves through a far quieter world. One profound change during this era is the increasing dominance of isolation. Dark energy continues to drive cosmic expansion. Galaxies, not gravitationally bound together, drift irreversibly beyond each other's horizons. Even the faint glow of distant structures fades away. In the far future, an observer within a gravitationally bound remnant, perhaps a merged supergalaxy, would see nothing beyond it. The observable universe would shrink to that isolated island of matter. Beyond the horizon, expansion accelerates relentlessly. Isolation deepens entropy's grip. Because without interaction, structure cannot reform. Energy gradients weaken. The cosmic temperature approaches near uniform coldness. And yet, change does not stop entirely. Even in darkness, quantum processes persist. Black holes remain, and their existence introduces the next crucial phase of the cosmic timeline. Because black holes are not eternal. In the 1970s, Stephen Hawking demonstrated that black holes are not perfectly black. Due to quantum effects near their event horizons, they emit radiation, now known as Hawking radiation. This radiation is incredibly weak for large black holes. A supermassive black hole might take 10 to the power of 100 years or more to fully evaporate. But the process is inexorable. Black holes lose mass. Slowly, imperceptibly at first, over spans so vast that human language struggles to contain them. The degenerate era may last until roughly 10 to the power of 40 years, if protons decay, which we will explore next, or much longer if they do not. But eventually, stellar remnants either decay, collide, or are absorbed by black holes. Matter becomes rarer. The universe grows colder and more dilute. This era is sometimes described as peaceful. But it is not peaceful in a comforting way. It is quiet because complexity is gone. There are no bright suns warming planets. No active galactic cores blazing. No chemical cycles driving life. Only the slow cooling of matter and the faint whisper of quantum processes. Time continues to flow in the geometric sense. Space-time still extends. Entropy still increases. But the richness that once marked cosmic history fades. The degenerate era represents a universe that is no longer creative. It is archival, holding onto remnants, drifting toward simplicity. And here, a new question emerges. What happens to matter itself over such immense spans? Because some theories suggest that even protons, the building blocks of atoms, may not be eternal. If protons decay, then white dwarfs, neutron stars, and even black dwarfs will eventually dissolve into radiation. If they do not decay, gravitational interactions may still reduce structure over unimaginable timescales. Either way, matter does not remain unchanged forever. And as matter dissolves or collapses, entropy approaches its maximum. The universe grows darker, more uniform, more still. We are not yet at the end of time, but we are watching time lose its intensity. The cosmic clock ticks, but each tick marks less and less change. In the next chapter, we will examine proton decay, a process that, if confirmed, would mean that even the most stable atoms are temporary. Because if matter itself is not permanent, then the end of time becomes not just a matter of stars fading, but of substance dissolving. For everything we see around us, stars, planets, dust, even our own bodies, there is a quiet assumption embedded in our intuition that matter is stable. Atoms may rearrange, molecules may break and reform, stars may explode. But protons, the building blocks of atomic nuclei, seem permanent. They form hydrogen, the most abundant element in the universe. They sit at the core of every heavier element forged in stars. If protons endure forever, then matter can, in principle, persist indefinitely. But physics does not guarantee that permanence. Some theories that attempt to unify the fundamental forces, known as grand unified theories, predict that protons are not absolutely stable. They may decay, albeit over inconceivably long timescales. Experimental searches for proton decay have placed lower limits on the proton's lifetime at around 10 to the power of 34 years or more. That is already trillions upon trillions of times longer than the current age of the universe. Yet if proton decay does occur, it changes everything about the far future. Because if protons decay, atoms cannot survive indefinitely. White dwarfs, neutron stars, black dwarfs, even the densest stellar remnants, would slowly disintegrate into lighter particles and radiation. Imagine a white dwarf drifting in darkness trillions of years from now. Its fusion reactions ended long ago. It has cooled nearly to the temperature of the cosmic background. It sits as a dense, inert sphere of degenerate matter. If protons decay, that sphere is not eternal. Over vast spans, perhaps 10 to the power of 36 or 10 to the power of 37 years, its atoms would slowly break apart. The solid structure would erode not from outside forces, but from within. Matter would transform into lighter particles such as positrons and neutral mesons, which would quickly decay further. The once solid remnant would gradually dissolve into radiation. Entropy would increase again, not through dramatic events, but through quiet transformation. Neutron stars would meet a similar fate. Though neutrons are slightly different from protons, they are related through the strong and weak nuclear forces. If protons are unstable under unified interactions, neutron-rich matter would also eventually decay. Over unimaginable durations, structured matter would thin into diffuse radiation. The universe would become increasingly uniform. This possibility is not confirmed. Proton decay has not yet been observed. It may not occur. But even if protons are stable, gravitational interactions over extremely long timescales will still reduce structure. Stars may collide. Remnants may be ejected from galaxies. Matter may spiral into black holes. Either way, the density of structured matter declines, and what remains grows simpler. If proton decay is real, then by roughly 10 to the power of 40 years, most conventional matter would be gone. Not violently destroyed, but slowly erased. What does this mean for time? Entropy continues to rise. Structure continues to fade. But the rate of meaningful events slows dramatically. Each decay event increases entropy slightly. Each disintegration releases tiny amounts of energy into expanding space. But these events become rarer. The universe becomes a sparse scattering of radiation and black holes. If proton decay does not occur, matter may last longer, perhaps until gravitational interactions gradually funnel everything into black holes. But even then, the end state is similar. Black holes dominate, and black holes are not eternal either. This phase of cosmic history, sometimes called the black hole era, will last far longer than the degenerate era. Supermassive black holes may persist for 100 years before evaporating through Hawking radiation. But once proton decay removes most conventional matter, black holes become the primary repositories of mass energy. And that sets the stage for the final act of cosmic change. In this long descent towards simplicity, something subtle happens to time. At first, entropy rises quickly. Stars burn brightly, galaxies merge, black holes collide. But as structure fades, entropy approaches its maximum asymptotically. The closer the universe gets to equilibrium, the slower meaningful change becomes. Entropy still increases, but the increase becomes infinitesimal. Imagine a universe composed only of sparse radiation and a few black holes drifting in near-perfect isolation. Between rare events, perhaps separated by spans of 10 to the power of 60 or 10 to the power of 70 years, nothing significant occurs. If an event happens once every 10 to the power of 80 years, does time between events still feel meaningful? For observers, if any could exist, time would stretch into near emptiness. But by this era, observers are impossible. Life depends on energy gradients, on stars, on chemical complexity. All of that is long gone. Time continues geometrically, but experiential time has ended. Thermodynamic time weakens. Only the slow evaporation of black holes remains to drive change. And when that process concludes, the universe may approach its final thermodynamic equilibrium. In the next chapter, we enter the black hole era, where the last structured objects in the cosmos slowly radiate away. Because once black holes evaporate, there may be nothing left to measure time at all. After stars have burned out, after galaxies have thinned, after matter has dissolved or collapsed, what remains? Black holes. They are the final strongholds of structure in the universe. While stars radiate energy quickly and matter may decay slowly, black holes endure. Their gravity dominates their surroundings. Their event horizons mark the final boundaries of trapped matter and light. In the far future, perhaps after 10 to the power of 40 years, if proton decay occurs, nearly all conventional matter will either have decayed into radiation or fallen into black holes. What remains is a sparse cosmos populated primarily by those dark gravitational giants. Supermassive black holes, once anchored at the centers of galaxies, will have absorbed much of the remaining mass in their local regions. Stellar mass black holes, formed from collapsed stars long ago, will drift through space, occasionally merging or interacting gravitationally over vast timescales. But eventually, even mergers become rare. Expansion continues. Dark energy stretches space-time relentlessly. Black holes become increasingly isolated. And here we encounter one of the most profound discoveries of 20th century physics. Black holes are not eternal. In 1974, Stephen Hawking combined principles of quantum mechanics with general relativity and revealed something extraordinary. Black holes emit radiation. This radiation arises from quantum fluctuations near the event horizon. Virtual particle pairs constantly pop into existence due to quantum uncertainty. Normally, they annihilate almost instantly. But near a black hole's event horizon, one particle may fall inward while the other escapes. To a distant observer, it appears as though the black hole is emitting radiation. This process is unimaginably slow for large black holes. A stellar mass black hole may take around 10 to the power of 67 years to evaporate completely. A supermassive black hole, millions or billions of solar masses, may persist for 10 to the power of 100 years or more. These numbers are so large that they stretch beyond ordinary comprehension. 10 to the power of 100 years is far longer than the age of the universe multiplied by itself billions of times. But the key insight is this: black holes slowly lose mass. They shrink, and eventually they disappear. As they evaporate, they emit increasingly energetic radiation. The smaller they become, the hotter they grow. The process accelerates toward the end. In the final moments of evaporation, a black hole may release a burst of radiation, the last gasp of concentrated mass energy that once defined it. And then it is gone. No structure remains, no event horizon, no trapped information, at least in classical description. After the last black hole evaporates, the universe contains almost nothing but extremely low-energy radiation, and perhaps a few stable particles, depending on whether proton decay occurs and what the ultimate stable configurations are. Entropy is nearly maximized. Energy is evenly distributed. Temperature approaches uniformity. There are no more dense objects to radiate meaningfully. No more gravitational engines. No more nuclear fusion. Only thin, dilute radiation stretched across an expanding spacetime. This era may last beyond 10 to the power of 100 years. But it is not dynamic. It is a slow fade. And with the evaporation of the last black hole, we approach something extraordinary. A universe with no stars, no planets, no atoms, no black holes, no structure. Only radiation drifting endlessly in an expanding void. Here, entropy has effectively reached its maximum possible value for the given conditions. There are no gradients left to drive change, no heat flows, no pressure differences, no gravitational collapses, no meaningful processes. And now the central question sharpens. If nothing changes, if no events occur, if no structures form or decay, does time still exist? Geometric time may continue in equations. Space-time coordinates may extend arbitrarily forward. But thermodynamic time, the arrow driven by entropy, has flattened. There is no further increase possible. The universe has reached equilibrium, and equilibrium is static. It is not that clocks stop ticking. It is that there are no clocks left to tick, no atoms to vibrate, no observers to measure, no events to distinguish one moment from the next. In such a state, and the difference between 1 second and 1 trillion years becomes physically meaningless, because nothing happens in between. Time becomes indistinguishable from timelessness. This is the concept of heat death, not an explosion, not a collapse, but a quiet asymptotic stillness. But before we declare time finished, we must consider alternatives. Is heat death inevitable? Could dark energy change? Could space-time tear itself apart? Could the vacuum of the universe decay into a new state? In the next chapter, we explore alternative cosmic endings, because the end of time may not be silent equilibrium. It might be far more dramatic, or far more sudden, and the future of time itself depends on which path the universe takes. So far, the future we have traced has been gradual. Stars fade, matter decays. Black holes evaporate. Entropy rises. The end of time appears as a slow thinning of change. But what if the universe does not drift gently toward equilibrium? What if the very expansion of the space-time accelerates beyond control? The expansion of the universe is driven by something we call dark energy, a mysterious component that makes up roughly 70% of the cosmos. Observations show that the expansion is accelerating. Galaxies are not merely moving apart. The rate at which they separate is increasing. In our current best model, dark energy behaves like a cosmological constant, a fixed energy density of empty space. If this is true, the universe will continue expanding forever at an accelerating rate, but not catastrophically. However, there is another possibility. Dark energy might not be constant. It might grow stronger over time. If dark energy's pressure becomes increasingly negative, if it exceeds a certain threshold, then expansion could accelerate without bound. This scenario is known as the Big Rip. In a Big Rip universe, space-time itself stretches faster and faster until gravitationally bound systems can no longer hold together. The sequence would unfold dramatically. First, galaxy clusters would be torn apart. The expansion would overpower the gravitational bonds between galaxies. Later, individual galaxies would be shredded. Stars would drift away from one another as gravity fails to keep them bound. Then, planetary systems would dissolve. Planets would drift away from stars. Eventually, expansion would overcome even the electromagnetic forces holding atoms together. Atoms would disintegrate. Nuclei would separate. Space-time itself would stretch so violently that even the smallest structures could not survive. And at the final moment, space-time curvature would diverge toward infinity. Time, in the geometric sense, would end at a finite future moment, a singularity not in the past, but in the future. The Big Rip is not currently supported by strong evidence. Observations suggest dark energy behaves very closely to a cosmological constant, but uncertainties remain. If dark energy's equation of state parameter, the ratio of its pressure to its energy density, is slightly less than -1, then the Big Rip becomes possible. In such a universe, the end of time would not be a fade into equilibrium. It would be a deadline, a calculable future date when expansion becomes infinite. Some theoretical estimates suggest that if the Big Rip were real, galaxy clusters might dissolve billions of years before the final moment. Solar systems would disintegrate minutes before the end. Atoms would be torn apart fractions of a second before space-time reaches infinite expansion. This is an extraordinary idea. It suggests that time itself could terminate not because nothing happens, but because everything happens at once. The structure of space-time would break, and with it, the meaning of duration. But even this scenario raises deeper questions. If space-time reaches a singular end state, does time stop because there are no further coordinates? Or does the concept of time simply become undefined beyond that boundary? Singularities signal breakdowns in our equations. Just as the Big Bang singularity indicates the limits of general relativity in the past, a Big Rip singularity would indicate limits in the future. Perhaps quantum gravity would intervene before space-time tears apart completely. Perhaps the equations predicting the rip would soften under a deeper theory. Or perhaps the rip would occur exactly as described. But even if the Big Rip does not happen, the possibility reminds us of something important. The end of time is not guaranteed to be gentle. It depends on the nature of dark energy. And dark energy remains one of the greatest mysteries in modern cosmology. We do not know why it exists. We do not know why it has the value it does. We do not know whether it will remain constant forever. If dark energy evolves, then the fate of time evolves with it. And so the question remains open. Will time fade into stillness? Or will it be torn apart? In the next chapter, we explore another alternative, one where the universe does not expand forever, but reverses direction. Because time may not only end, it might restart or cycle. And that possibility leads us to the idea of the Big Crunch and cosmic rebirth. For most of the 20th century, cosmologists believed the universe's expansion might eventually slow down. Gravity pulls matter together. If the universe contained enough matter and energy that gravitational pull could overcome expansion, the cosmic stretching would decelerate, halt, and reverse. Galaxies would begin drifting back toward one another. Cosmic expansion would turn into contraction, and over billions upon billions of years, the entire universe would collapse inward. This scenario is known as the Big Crunch. In a Big Crunch universe, time does not fade into equilibrium. It accelerates toward density. As contraction proceeds, galaxies merge more frequently. Radiation grows hotter, matter compresses. Entropy still increases, but the scale of physical interaction intensifies. Eventually, the universe could approach a state similar to the Big Bang, a hot, dense condition where space-time curvature becomes extreme. But here, we must be careful. The Big Crunch does not simply rewind time. Even if the universe contracts, entropy does not decrease. The arrow of time would still point forward toward higher entropy. The collapse would not be a reverse of cosmic history. It would be a new path toward maximum disorder under compression, and at the final moment of contraction, general relativity predicts a singularity, infinite density, infinite curvature. Just as the Big Bang represents a boundary in the past, the Big Crunch would represent a boundary in the future. Time in this picture ends not in dilution, but in compression. But there is another idea layered atop this one. Some cosmological models suggest that the Big Crunch might not be the final state. Instead, the collapse could transition into a new expansion phase, a cosmic bounce. In such cyclic models, the universe does not begin or end absolutely. It oscillates, expands, contracts, rebounds. Time, then, may not have a single beginning or a single ending. It may be part of a larger repeating structure. In certain quantum gravity frameworks, the singularity of a Big Crunch could be avoided. Instead of infinite density, quantum effects might prevent collapse beyond a certain scale. The universe could reach a minimum size and then expand again. This is sometimes referred to as a big bounce. If such a bounce occurs, what happens to time? Does time continue smoothly through the contraction and expansion? Or does each cycle represent a new beginning? Some speculative theories suggest entropy could reset during a bounce, though this remains controversial and highly theoretical. More commonly, entropy would accumulate across cycles, making each subsequent universe more entropic than the last. But here we encounter a deeper issue. Observations currently indicate that our universe's expansion is accelerating due to dark energy. For a Big Crunch to occur, dark energy would need to change behavior, perhaps reverse sign, or weaken significantly. There is no current evidence that this will happen, which makes the Big Crunch less likely under present data. Yet, cosmology is not static. Dark energy remains mysterious. Its properties may evolve over cosmic time, and if expansion ever reverses, time's trajectory would transform dramatically. Instead of drifting toward silence, the universe would move toward intensity, toward heat, toward compression, toward an endpoint of curvature. In such a universe, the end of time would not be quiet equilibrium. It would be a final convergence. But whether that convergence leads to termination or renewal depends on physics we'd not yet fully understand. The Big Crunch reminds us of something profound. The fate of time depends entirely on the geometry of space-time itself. If space-time stretches forever, time may fade. If space-time tears, time may rip apart. If space-time contracts, time may culminate in collapse. And if space-time cycles, our time may not have a final ending at all, only transitions. But even these dramatic possibilities assume space-time remains intact. There is one more scenario, quieter in prediction, but potentially instantaneous in effect. A scenario in which the universe ends not by stretching or collapsing, but by shifting, because the vacuum itself may not be stable. And if the vacuum changes, everything changes. In the next chapter, we explore vacuum decay, a possibility where time does not slowly fade, nor violently rip, nor cyclically bounce, but abruptly reconfigure. And in that scenario, the end of time could arrive without warning. Everything we have discussed so far assumes something fundamental, that the vacuum of space, empty space itself, is stable. But what if it is not? In quantum field theory, empty space is not truly empty. It is filled with fluctuating fields. Particles arise as excitations of those fields. The vacuum state we experience is simply the lowest energy configuration currently accessible. But lowest may not mean absolute lowest. It may mean metastable. Imagine a ball resting in a shallow valley. It appears stable. It sits comfortably at the bottom. But nearby, there may be a deeper valley separated by a small ridge. If the ball gains enough energy to cross that ridge, it will roll downward into a lower state. The vacuum of our universe may be like that. It may be sitting in a local minimum, not the true minimum. If that is the case, then a quantum fluctuation could one day trigger a transition. This event is known as vacuum decay. If vacuum decay occurs, a bubble of true vacuum would form. Inside that bubble, the fundamental constants of nature could change. The strengths of forces, the masses of particles, even the structure of space-time itself might be different. And this bubble would expand at nearly the speed of light. There would be no warning, no visible approach, no signal arriving ahead of it. One moment, the universe would exist as it does now. The next, a new vacuum state would replace it. Atoms might no longer hold together. Chemistry might become impossible. Stars, matter, life, all would dissolve instantly as physical laws shift. From our perspective, time would simply end. Not because clocks stopped, not because entropy reached maximum, but because the framework supporting physical processes changed. It is important to emphasize that vacuum decay is speculative. Our current measurements of the Higgs boson and other parameters suggest that our vacuum may indeed be metastable, though with lifetimes vastly exceeding the current age of the universe. If metastable, vacuum decay could occur at any moment, or not for trillions upon trillions of years, or perhaps never. But the unsettling feature is this: it would not depend on cosmic expansion. It would not depend on entropy. It would not depend on stars dying. It would be a quantum event, a fluctuation, and it would propagate outward at light speed, rewriting reality as it goes. In this scenario, time does not fade. It does not rip. It does not collapse. It simply terminates. The arrow of time ceases because the physical structure supporting causality changes. There would be no observer to experience the transition. The bubble would arrive at light speed. The laws governing atoms would shift before neural signals could propagate. From any local frame of reference, time would not slow. It would not stretch. It would not reverse. It would just end. But even here, we must think carefully. Does time end because events stop occurring? Or because the geometry of space-time changes? Or because the meaning of cause and effect dissolves? Vacuum decay challenges our intuition, not because it is violent, but because it is final. It suggests that time's continuity depends on the stability of physical law itself. If the vacuum is stable, time may stretch indefinitely. If it is metastable, time's existence is conditional. Conditional on quantum stability. Conditional on field configurations. Conditional on probabilities. Which means time may not be as inevitable as it feels. It may persist only because the vacuum remains in its current state. This possibility does not make the universe fragile in a practical sense. The predicted lifetimes are unimaginably long, but it reveals something profound. Time is not separate from physics, it is emergent from it. If the underlying fields change, time changes. If space-time geometry shifts, time shifts. If entropy gradients vanish, time fades. And so, the end of time is not a single event. It is a collection of possibilities: heat death, big rip, big crunch, vacuum decay. Each describes a different way in which time might lose meaning, or structure, or continuity. But beneath all of these scenarios lies a deeper philosophical question. If nothing changes, if no observers remain, if no events distinguish one moment from another, is time still there? Or is time simply the measure of change? In the next chapter, we leave cosmology behind for a moment and examine time itself, not as a cosmic process, but as a relational concept. Because the end of time may not require cosmic catastrophe, it may only require stillness. Imagine a universe in perfect equilibrium. No stars burning, no black holes evaporating, no particles decaying, no radiation gradients, no motion that leads to transformation. Energy is evenly distributed across space. Temperature is uniform. Every region is statistically identical to every other region. Nothing happens. Now ask yourself carefully, if absolutely nothing changes, does time still exist? This is the deepest version of our question. Because perhaps the end of time does not require a big rip or vacuum decay. Perhaps it only requires the end of change. In physics, time is closely tied to measurement. We define seconds by atomic oscillations. We define duration by periodic motion. But these are physical processes, changes in state. Without change, no clock can tick. But one might argue that time still passes, even if nothing happens. In classical Newtonian thinking, time exists independently. It flows regardless of events. But modern physics complicates this idea. In relativity, time is part of space-time geometry. It is not something that flows, it is something that exists as a dimension. Events are laid out along world lines. The passage of time may be a feature of how we experience that dimension. In thermodynamics, time's arrow depends on entropy increase. If entropy stops increasing, if it reaches maximum, then the arrow of time disappears. And in quantum gravity approaches, time may not be fundamental at all. It may emerge from correlations between systems. In some formulations, the fundamental equations describing the universe do not even contain a time variable. Instead, time arises from change within the system. If that is true, then in a universe with no change, time may not have meaning. It would still exist geometrically in equations, but physically, it would be indistinguishable from timelessness. Consider this carefully. If every particle in the universe is in equilibrium, if no interactions alter the overall state, if no gradients allow work to be done, then what distinguishes one moment from the next? The answer may be nothing. In such a universe, you could label moments with coordinates T1, T2, T3, but there would be no observable difference between them. They would be identical slices of space-time. Time would exist mathematically, but not dynamically. This idea is sometimes described as the frozen universe problem. If the fundamental description of the cosmos is static, then time may be a feature of how subsystems evolve relative to each other, not an absolute background parameter. Without evolving subsystems, time dissolves into abstraction. This brings us back to entropy. Entropy increases because energy spreads out and becomes less available to do work. But when entropy reaches maximum, no further spreading can occur. Equilibrium is reached, and equilibrium is static. There is no preferred direction, no arrow, no irreversible processes. In such a state, the difference between the future and the past becomes meaningless. Not because equations break, but because physical distinction vanishes. This may be the quietest version of the end of time. No explosion, no collapse, no singularity. Just the gradual approach to stillness. Over unimaginable spans, 10 to the power of 100 years and beyond, black holes evaporate. Radiation spreads thinner as space expands. The cosmic temperature asymptotically approaches absolute zero. And then, nothing new happens. The universe becomes a near-perfect equilibrium state. One might ask, could quantum fluctuations still occur? Perhaps extremely rarely, random fluctuations might create small pockets of temporary structure, so-called Boltzmann fluctuations. Given infinite time, improbable events may eventually occur. But these fluctuations would be rare beyond comprehension. They would not represent sustained structure. They would not create lasting gradients. And even their existence is debated. So we arrive at something subtle. The end of time may not be a final moment. It may be a final state. A state in which the distinction between moments disappears. Time does not stop. It becomes irrelevant. And perhaps that is the most profound idea of all. Because throughout cosmic history, time has been defined by change. Stars forming, galaxies merging, black holes colliding. But once all gradients vanish, once all structure dissolves, once entropy maximizes, the universe may continue geometrically, but dynamically it is complete, finished, not destroyed, not rewritten, simply done. And in that quiet completeness, the concept of before and after may no longer describe anything real. In the next chapter, we take one final step beyond physics and ask a deeper question. If time can fade into irrelevance, what does that say about the present moment? Because understanding the end of time changes how we understand the now. When we speak of the end of time, we are really speaking of the end of change, the end of gradients, the end of structure. But right now, in this moment, time is anything but silent. Stars are burning, galaxies are merging, entropy is rising, neurons are firing, breath is moving in and out of lungs. The future we have traced, trillions, quadrillions, and unimaginable powers of 10 into the distance, feels abstract because it is so far removed from our scale. Yet the laws governing that distant future are the same laws governing this moment. The arrow of time that will one day flatten into equilibrium is the same arrow that allows memory to exist. Entropy increases in the fusion core of the sun. Entropy increases in your metabolism. Entropy increases in the radiation escaping into space. Time's direction today is the same direction that will eventually carry the universe toward stillness, which raises a subtle and profound thought. The end of time is not separate from the present. It is the continuation of the same process already underway. The difference lies only in scale. In the stelliferous era, time feels vibrant because energy gradients are strong. The temperature difference between the sun and space drives fusion. The chemical differences inside living systems drive metabolism. The cosmic microwave background is warmer than absolute zero. Change is abundant. But as gradients weaken, time's intensity weakens with them. The end of time is not an event imposed from outside. It is the asymptotic completion of entropy's work. And yet, there is something extraordinary about the present. We live at a time when stars still shine, when galaxies are still visible, when complexity still flourishes. Cosmologists sometimes note that we exist during a uniquely informative era. In the far future, distant galaxies will drift beyond observable horizons. The cosmic microwave background will redshift into undetectability. Evidence of the Big Bang may disappear from view. Future civilizations, if they exist trillions of years from now, may not even know the universe once expanded. We are living in a window of cosmic clarity. Time feels ordinary because we are immersed in change. But change is temporary. The processes that define time's arrow are finite. Fusion fuel is finite. Black hole mass is finite. Gradients are finite. What makes the idea of the end of time so unsettling is not just its scale. It is the recognition that time depends on structure, and structure is temporary. Yet there is also comfort in this. The laws of physics do not point toward chaos without reason. They describe a universe that evolves coherently from low entropy toward equilibrium. The end of time is not a mistake, it is a consequence. The same physics that allows galaxies to form ensures they will one day fade. The same thermodynamics that drives life ensures that life is temporary. The end of time does not negate the present. It contextualizes it. Every second we experience is part of a larger thermodynamic arc stretching from the Big Bang to eventual equilibrium. Time feels precious precisely because it is directional, because moments cannot be repeated, because entropy increases. If the universe were static and unchanging, there would be no narrative, no story, no memory, no evolution. The end of time, then, is not simply a far future curiosity. It reveals something fundamental about now. We are living in a universe where gradients still exist, where entropy still has room to rise, where time still carries meaning because change still happens. In the far future, when equilibrium reigns, there will be no such meaning. But here, in this fleeting window of cosmic history, time is alive, which brings us to the final layer of our journey. If time may eventually fade into irrelevance, and if the arrow of time is tied to entropy, and if space-time itself may be emergent, then perhaps time is not a permanent feature of reality. It may be a phase, a property of a universe out of equilibrium. And when equilibrium arrives, time does not break. It dissolves. In the final chapter, we will bring everything together, from cosmology to thermodynamics to quantum theory, and answer the question fully. What does it truly mean to say that time ends? Not dramatically, not metaphorically, but physically. And when we say the end of time, we must be precise. Time does not shatter like glass. It does not freeze like a broken clock. It does not explode outward in visible fragments. The end of time in physics is not an event. It is a condition. To understand that condition, we return to the three layers we uncovered earlier. First, geometric time, the dimension embedded in space-time. Second, thermodynamic time, the arrow defined by entropy increase. Third, experiential time, the perception created by memory and change. Each layer ends differently. Geometric time, according to relativity, continues as long as space-time continues. If the universe expands forever, the space-time manifold may extend indefinitely. Coordinates can always be labeled further along a future direction. But labeling coordinates does not guarantee meaningful difference. Thermodynamic time depends on entropy gradients. As long as entropy can increase, time has direction. When entropy reaches maximum, direction dissolves. There is no further asymmetry. Experiential time depends on observers. Without life, without consciousness, without memory formation, there is no lived sense of duration. The end of time may not mean space-time disappears. It may mean entropy finishes its work. Let us imagine the final state under the most conservative scenario. Heat death. All stars have burned out. All matter has decayed or fallen into black holes. All black holes have evaporated. Only extremely dilute radiation remains, spread nearly uniformly across an ever-expanding cosmos. Temperature differences are negligible. Energy gradients are effectively zero. No process can extract useful work. No complex structure can form. No sustained fluctuations occur. In this state, entropy is maximized. What changes from one moment to the next? Nothing measurable. If nothing changes, time has no arrow. If time has no arrow, the distinction between earlier and later becomes physically meaningless. Geometric time may still exist in equations, but dynamic time, the time of processes, is gone. It is not that time stops. It is that nothing moves through it in a way that creates difference. And difference is what gives time meaning. This distinction is subtle but crucial. The end of time is not about clocks ceasing to tick. It is about the universe reaching a state where ticking is impossible, because ticking requires gradients. Gradients require inequality. Inequality requires structure, and structure is temporary. Time, then, may not be fundamental. It may be emergent, an emergent feature of systems far from equilibrium. As long as the universe is evolving, forming stars, collapsing gas clouds, radiating energy, time feels alive. When evolution ceases, time becomes inert. This perspective reshapes the question entirely. We often imagine the end of time as a dramatic last second, but physics suggests something quieter. Time fades into irrelevance. It does not need to terminate at a boundary. It only needs to become indistinguishable from stasis. In a universe where every region is identical, every particle distribution static, every energy gradient exhausted, the difference between 1 trillion years and the next trillion years becomes undefined. Nothing marks the passage. Time becomes a coordinate without content, and this may be the ultimate fate of the cosmos. Not annihilation, not collapse, not ripping, but completion. Entropy completes its rise. Space-time continues geometrically, but dynamically the universe is finished. And so we reach a remarkable conclusion. The end of time is not a singularity in the future. It is the logical completion of thermodynamics. It is not an abrupt event. It is an asymptotic condition, and it is already written into the equations that govern stars and atoms today. In the next chapter, we will take one final step, asking whether time itself might not be fundamental at all. Because if time is emergent, then perhaps the end of time is not an ending, but a return to something deeper. There is a growing idea in modern theoretical physics that may change the entire framing of our question. What if time is not a fundamental ingredient of reality? What if it is not woven into the universe at the deepest level? What if time is something that emerges, like temperature or pressure, from more basic underlying structures? To understand this, consider temperature. Temperature feels fundamental. We measure it constantly. It affects matter in obvious ways, but temperature is not a basic property of a single particle. It emerges from the collective motion of many particles. A single atom does not have temperature in isolation, or temperature arises statistically. Some physicists suspect that time may be similar. At the deepest level, in certain formulations of quantum gravity, the fundamental equations do not contain a time variable at all. Instead, they describe relationships between configurations. Time emerges from correlations between subsystems. In other words, time may not be the stage upon which physics plays out. It may be a pattern that appears when parts of the universe interact. In the Wheeler-DeWitt equation, a candidate equation for quantum gravity, time does not appear explicitly. The equation describes a static wave function of the universe. From that static description, time must somehow arise. This is sometimes called the problem of time in quantum gravity. If the fundamental description of the universe is timeless, then time as we experience it must emerge from entanglement, from correlations, from entropy, which means time only exists when systems are far from equilibrium, when change occurs, when information flows. In a universe that has reached maximum entropy, complete equilibrium, there are no evolving correlations, no gradients, no structure forming or dissolving. In that state, if time is emergent, it may simply disappear, not because something stops it, but because the conditions that generate it no longer exist. This reframes the end of time. Time does not need to end as a fundamental dimension. It only needs to stop emerging. Just as temperature ceases to have meaning in a system of one particle, time may cease to have meaning in a universe with no change. And perhaps this has always been the case. Perhaps time emerged shortly after the Big Bang, when the universe began evolving from a low entropy state. Before that, if before even makes sense, time may not have existed in any meaningful way. And in the far future, after equilibrium is reached, time may dissolve back into that timeless foundation. The beginning and end of time may mirror one another. At the beginning, entropy was minimal. Structure had not yet formed. The arrow of time began when the universe started evolving away from uniformity. At the end, entropy will be maximal. Structure will have dissolved. The arrow of time will flatten. In between these two states lies the entire history of cosmic change. Time, then, may be a phase of the universe, not eternal, not independent, but contingent, emergent, temporary. This idea carries profound implications. If time is emergent, then asking when does time end may be like asking when does temperature end. The answer is when the conditions that give rise to it disappear. In equilibrium, temperature differences vanish. In equilibrium, time differences may vanish. The universe becomes a static configuration, not frozen in a dramatic sense, but complete. Nothing distinguishes one slice from another. Nothing evolves, nothing accumulates, nothing decays. It is not destruction, it is cessation of dynamical distinction. And so we arrive at perhaps the most subtle answer to our original question. The end of time is not necessarily a final tick. It is the disappearance of meaningful sequence. And that disappearance is written into the logic of entropy itself. Yet, even here, uncertainty remains. Our understanding of quantum gravity is incomplete. We do not yet know whether space-time is fundamental or emergent. We do not know whether dark energy is constant or dynamic. We do not know whether vacuum decay is possible. We do not know whether new physics will intervene before equilibrium, which means the end of time remains theoretical. But its possibility is not mystical. It is mathematical. And mathematics suggests that the arrow of time cannot rise forever. In the next chapter, we step into the final reflection, not about the mechanics of ending, but about perspective. Because when you understand that time may one day fade, the present moment feels different. If time may one day fade into stillness, if entropy may one day flatten all difference, if stars, matter, and even black holes are temporary phases, then what are we living inside right now? We are living inside a temporary river. Time feels constant because we are surrounded by change. The earth rotates. The sun burns. Our bodies metabolize. The cosmic background still glows faintly from the early universe. Everywhere we look, gradients exist, differences in temperature, pressure, density, energy. These gradients drive motion. Motion creates events. Events create sequence. Sequence creates time as we experience it. But from the perspective of the far future, this era is fleeting. The stelliferous era, the age of stars, will last perhaps 100 trillion years. That sounds immense, but compared to the 100 to the power of a 100-year lifetime of supermassive black holes, it is a brief chapter. And compared to an infinite future of equilibrium, it is almost nothing. We exist in a rare window where the universe is far from equilibrium, where complexity flourishes, where entropy is rising rapidly because gradients are strong. This is not the default state of reality. It is a transient one. The early universe began in extraordinary simplicity. Smooth, hot, uniform. Over billions of years, structure emerged, galaxies formed, stars ignited, planets coalesced, chemistry evolved, life appeared. All of this depends on the arrow of time. But the arrow of time itself depends on low entropy at the beginning, which means that the vibrant world we inhabit is balanced between two extremes: the low entropy simplicity of the past and the high entropy simplicity of the future. In between lies complexity. In between lies narrative. In between lies history. Time, as we experience it, exists because the universe is not finished, because gradients still exist, because entropy has room to grow. But that growth is finite. Every star that burns reduces available fuel. Every black hole that evaporates spreads mass energy thinner. Every expansion of space dilutes radiation further. The river flows toward stillness, and yet within that flow extraordinary patterns arise. Consciousness, memory, culture, science, the ability to ask whether time will end. Perhaps the most remarkable feature of time is not that it flows, but that within its flow awareness arises. We are part of the thermodynamic process. Our thoughts consume energy. Our brains generate entropy. Our existence is possible only because of gradients created by stars. We are not separate from time's arrow. We are products of it, which makes the question of time's end deeply personal. When time fades in the far future, there will be no observers left to contemplate it. The universe will not mourn its stillness. It will simply be. The end of time, then, is not tragic. It is impersonal. It is the logical conclusion of physical law. But knowing that does something subtle to the present. It reframes urgency. It reframes permanence. It reveals that what feels constant is contingent. Time feels endless on human scales, but a cosmology shows it may be temporary. This does not make the present smaller. It makes it rarer. We are living in the era when time still carries momentum, when structure still forms, when the night sky still contains billions of galaxies. Trillions of years from now, even the evidence of the Big Bang may be gone. Future observers, if any could exist, might see only an isolated galaxy in darkness, unaware of the vast cosmic history that preceded them. But we can see it. We live in the era of visibility, in the era of measurable expansion, in the era when entropy is still rising dynamically. And perhaps that is the quiet gift of understanding the end of time. It teaches us that time is not guaranteed. It is emergent. It is directional. It is temporary. And within that temporariness lies everything we call experience. The river of time will eventually reach still water. But for now, it flows. In the next chapter, we take our final step not into speculation, but into stillness, and answer the question fully and calmly. Does time truly end? Or does it simply become indistinguishable from infinity? When we imagine the end, we imagine a boundary, a final second, a last tick of the cosmic clock, a moment after which there is nothing. But the universe does not always offer clean edges. It often offers asymptotes, limits that are approached but never violently crossed. If the universe expands forever, if entropy increases toward a maximum, if black holes evaporate over unimaginable spans, then the end of time may not be a sharp cutoff. It may be a horizon that is never reached in a dramatic sense. Entropy increases asymptotically. It approaches a maximum. But the closer it gets, the slower change becomes. Processes stretch across longer and longer durations. Events become rarer. Differences become smaller. Time does not slam into a wall. It thins. It stretches. It loses contrast. Imagine a universe 100 years in the future. All black holes have evaporated. Only extremely low-energy photons drift through expanding space. Temperature differences are nearly zero. No new structure forms. Quantum fluctuations may still occur, but they are rare beyond comprehension. Now imagine advancing another trillion years. What has changed? Perhaps almost nothing measurable. The universe is so dilute, so uniform, that distinguishing between vast spans becomes meaningless. At that scale, 1 year and 1 billion years may describe physically indistinguishable conditions, and if two durations cannot be distinguished by any physical process, are they meaningfully different? This is where the idea of infinity becomes subtle. If the universe continues expanding forever, time may extend infinitely in the mathematical sense. But if nothing changes during that infinity, then infinity collapses into sameness. Duration without difference becomes indistinguishable from timelessness. This may be the quiet truth behind heat death. Time does not need to stop. It only needs to lose content. In human life, we measure time by events: birthdays, seasons, heartbeats. Remove events, and time becomes abstract. The far future of the universe may be entirely abstract. Space-time may still exist geometrically. Coordinates may extend forward, but without change, those coordinates describe a static condition. The distinction between 10 to the power of 101 years and 10 to the power of 102 years may have no observable meaning. The universe may effectively enter a state where infinity and stillness overlap. And yet, one could argue that even in heat death, quantum fluctuations persist. Perhaps extremely rare fluctuations might momentarily lower entropy locally. Given infinite time, improbable events might occur. This leads to strange theoretical ideas like Boltzmann brains, spontaneous fluctuations creating temporary self-aware structures in an otherwise empty universe. But even these ideas highlight the same principle. Time in such a universe would be dominated by enormous stretches of nothing, punctuated by vanishingly rare events. And when events become separated by unimaginable intervals, the continuity of time dissolves. It becomes fragmented, sparse, nearly indistinguishable from non-existence. So does time end. If by end we mean a final boundary, perhaps not. If by end we mean the disappearance of meaningful sequence, almost certainly. And that difference matters, because it reframes the question. The end of time is not about whether the cosmic clock stops. It is about whether the universe continues to evolve. Evolution requires gradients. Gradients require structure. Structure is temporary. When structure fades, evolution ceases. When evolution ceases, time becomes empty. In that emptiness, infinity feels static, and static infinity feels timeless. Perhaps the end of time is not a final moment. Perhaps it is a final condition. A condition in which the difference between before and after becomes physically irrelevant. And that may be more profound than any dramatic ending, because it suggests that time is not the fundamental stage of reality. It is the expression of imbalance, the expression of unfinished thermodynamics, the expression of a universe still in motion. And when motion ends, time fades with it. In the next chapter, we take one final reflective step, returning to the present moment with everything we now understand. Because the knowledge that time may one day dissolve changes how we see now. After traveling trillions upon trillions of years into the future, after watching stars fade, matter decay, black holes evaporate, after imagining equilibrium so complete that time loses meaning, we return here, to now. And something feels different, because the present moment is not just another point in time. It is a rare configuration of the universe. We exist in a narrow thermodynamic window, a period when entropy is rising rapidly, when gradients are strong, when structure is abundant. This window is temporary. Before us lies a low entropy past. Ahead lies a high entropy future. Between them is complexity. Between them is narrative. Between them is life. Time feels natural because we are immersed in change. The sun radiates energy into cold space. That gradient powers weather, oceans, biology. Every heartbeat, every thought, every memory depends on energy flowing from hot to cold. We are not observers standing outside time. We are processes occurring within it. Our existence depends on entropy increasing. Without the arrow of time, there is no chemistry as we know it. Without chemical reactions, there is no metabolism. Without metabolism, there is no thought. The river of time is not just something we experience. It is something that sustains us. And yet, the same laws that make the present possible guarantee that this era is not permanent. The sun will exhaust its hydrogen in roughly 5 billion years. Red dwarfs will burn for trillions. But eventually, star formation ends. Eventually, gradients weaken. Eventually, equilibrium approaches. And the universe is not designed for permanence. It is designed for evolution. And evolution has an arc. What is extraordinary is not that time may end. What is extraordinary is that time exists at all. If the early universe had not begun in an extraordinarily low entropy state, there would be no arrow of time. If entropy were already maximal, there would be no change, no stars, no galaxies, no observers. The fact that time flows, that it has direction, is a consequence of cosmic initial conditions we still do not fully understand. The end of time is simply the completion of that direction. From low entropy to high entropy. From structure to equilibrium. From motion to stillness. But here, in this moment, entropy has not finished rising. Gradients remain. Stars shine. Life exists. Questions can be asked. And perhaps that is the most astonishing thing. We live during the era when time is still meaningful, when the universe is still dynamic, when history is still unfolding. From the perspective of the far future, this era is brief. From our perspective, it feels expansive. Time's scale is relative not just physically, but experientially. A human lifetime is insignificant on cosmic scales, but it is immense within lived experience. And that reveals something subtle. Time is not only measured by duration, it is measured by change. A century filled with transformation can feel vast. 1 trillion years of equilibrium may feel empty. So, when we speak of the end of time, we are not speaking of something that diminishes the present. We are speaking of something that frames it. Understanding that time may one day fade does not make the present fragile. It makes it rare. And rarity is not weakness, it is significance. We are living in a thermodynamic gradient, in a temporary river between two cosmic simplicities. And within that river, consciousness has emerged. The universe has become aware of its own temporal arc. And perhaps that awareness is itself part of entropy's journey. In the next chapter, we step into the final quiet conclusion, not dramatic, not apocalyptic, but calm. Because the end of time, as physics suggests, is not chaos, it is completion. When most people imagine the end of time, they imagine violence, explosions, collapsing stars, space-time tearing itself apart, a final second that shatters existence. But the most likely ending, according to our current understanding of physics, is not catastrophe, it is completion. The universe began in a state of extraordinary simplicity, hot, dense, smooth, low in entropy. From that simplicity emerged structure. Galaxies formed, stars ignited. Matter organized itself into increasingly complex configurations. Entropy increased. Time acquired direction. History unfolded. And throughout this unfolding, energy flowed from concentrated forms into more diffuse ones. Gradients flattened. Differences softened. Structure gradually gave way to uniformity. The end of time, in its quietest and most probable form, is not an interruption. It is the final chapter of that thermodynamic story. When stars no longer burn, entropy continues to rise. When matter decays or collapses, entropy rises further. When black holes evaporate, entropy approaches its maximum. Eventually, the universe reaches equilibrium, a state where no further work can be extracted, where no gradients remain, where no large-scale change is possible. In that state, nothing dramatic happens. There is no explosion marking the last second. There is no boundary where space-time tears open. There is only stillness. Stillness on scales so vast that motion becomes negligible. Temperature differences vanish. Energy spreads thin. Structure dissolves into statistical uniformity. And because time is defined by change, by difference, by the progression of entropy from low to high, its meaningful existence fades alongside those gradients. Time does not need to stop. It only needs to become indistinguishable from eternity. Imagine a universe so uniform that advancing it by 1 trillion years produces no observable difference. Imagine advancing it by 1 quadrillion more. Nothing changes. The coordinates of space-time may extend forward infinitely, but without events, without evolution, without structure, that infinity contains no narrative. It is not chaos, it is completion. And there is something strangely peaceful about that. The end of time is not destruction, it is equilibrium. It is the universe finishing its thermodynamic journey, from imbalance to balance, from complexity to simplicity, from motion to rest. And perhaps this reveals something profound. Time is not the ultimate foundation of reality. It is a phase, a property of a universe out of equilibrium. When equilibrium arrives, time does not shatter. It resolves. Just as waves resolve when wind stops blowing across water, the surface becomes smooth, not broken, not erased, simply calm. And this is the most likely fate of time under our current understanding. A gradual thinning of change, a slow fading of difference, a final state where before and after have no meaningful distinction. And in that sense, the end of time is not a moment. It is a condition that may last forever. In the final chapter, we will close our journey not by adding new speculation, but by resting in what we have learned. Because understanding the end of time changes how we understand existence itself. We began with a question. What would it mean for time to end? Not the end of Earth, not the end of the sun, not even the end of the universe as we know it, but the end of time itself. And after traveling across trillions upon trillions of years, through fading stars, dissolving matter, evaporating black holes, stretching space-time, and maximum entropy, we have arrived at something unexpected. The end of time is not a single event. It is a horizon where change becomes so rare, so thin, so diluted, that sequence loses meaning. A horizon where entropy has completed its rise. A horizon where structure has resolved into equilibrium. Time, as we experience it, depends on contrast, hot and cold, past and future, cause and effect, low entropy and high entropy. Without contrast, there is no direction. Without direction, there is no story. Without story, there is no lived sense of duration. In the far future, if heat death prevails, the universe will not collapse into chaos. It will not ignite in a final blaze. It will settle, gradually, into sameness. And in that sameness, time becomes indistinguishable from infinity. Not because it stops, but because nothing marks its passage. And perhaps that is the most important realization. Time is not something that flows independently of the universe. It flows because the universe is unfinished, because gradients exist, because entropy has somewhere to go, because stars still burn, because change still happens. The moment the universe finishes its thermodynamic journey, time loses its momentum. It becomes a coordinate without content, a dimension without evolution, a quiet expanse where the difference between moments dissolves. Yet there is no tragedy in this. The universe is not striving to preserve complexity forever. It is not resisting equilibrium. It simply follows the logic of its laws, from simplicity to complexity, from complexity back to simplicity, from imbalance to balance. And within that arc, time emerges and fades. We often fear endings because we experience them personally. But the cosmic end of time is not personal. It does not carry emotion. It is not loss. It is completion. And perhaps understanding that changes how we see the present. Because if time is temporary, if structure is temporary, if stars, galaxies, and even space-time itself are phases in a larger thermodynamic arc, then this era, this fleeting window of cosmic complexity, is extraordinary. We are living during the age of light, the age of stars, the age when entropy still rises dynamically, the age when the universe is interesting. One day, trillions upon trillions of years from now, equilibrium may reign. But right now, the river still flows. And in its flow, awareness has emerged. The universe has become capable of asking whether time will end. That question itself is part of the thermodynamic journey. And perhaps that is enough. In our final closing, we will not predict further. We will not speculate beyond physics. We will simply rest in the understanding that time is a phase of the universe. And phases, by definition, do not last forever. Yet while they exist, they are everything. And so we arrive where all journeys eventually lead, not to an explosion, not to a collapse, not to a final ticking second echoing into silence, but to stillness. The end of time, as physics most quietly suggests, is not an event. It is a settling, a universe that has completed its thermodynamic arc, a cosmos that has exhausted its gradients, a space-time stretched thin into near-perfect equilibrium. Stars will not scream as they fade. Black holes will not roar as they evaporate. Entropy will not announce its victory. Everything will simply become uniform. cold, even, indistinguishable. And in that indistinguishability, time loses its meaning. Because time is not just duration, it is difference, it is change. It is the asymmetry between what was and what will be. When that asymmetry disappears, the story ends, not violently, but naturally. And perhaps that is the deepest truth. Time is not eternal, it is emergent. It rises when the universe is out of balance. It fades when balance is restored. The Big Bang may have been the beginning of time, not because something ignited, but because entropy began to rise from an extraordinarily low state. And the end of time may arrive not because something breaks, but because entropy has finished rising. Between those two conditions, low entropy and high entropy, lies everything. Galaxies, stars, planets, life, memory, questions, you, this moment. The river of time is temporary, but while it flows, it carries complexity beyond imagination. We exist in a narrow band of cosmic history where gradients are strong enough to power consciousness, where starlight still warms planets, where the night sky still reveals billions of galaxies, where entropy still has room to grow. One day, trillions upon trillions upon trillions of years from now, equilibrium may reign. But no observer will be there to witness it, because observers require change, and change will be gone. And so, the end of time will not be experienced, it will not be remembered, it will not be feared, it will simply be. Or, perhaps more accurately, it will simply no longer matter. And here, in this quiet understanding, something shifts. And the end of time does not diminish the present, it magnifies it. Because we are living during the rare era when time still carries momentum, when history still unfolds, when the universe is still in motion, when difference still exists. The far future may belong to stillness, but now belongs to change. And change is what makes time meaningful. So, as you drift toward rest tonight, remember this. Time feels endless because we are immersed in it. But cosmology whispers that it is a phase, a beautiful, temporary unfolding between two cosmic simplicities. And while it lasts, it is everything. Thank you for journeying to the edge of time with me. Until our next quiet exploration of the universe, rest gently.